All right, and welcome back. So this is the start of part 1 of Thursday's lecture. So last time we left off, we were talking about motional EMF out of 20.5. So we started to set up the idea that if we had a wire moving through a magnetic field, that we could get the magnetic field to run a current through a wire, which of course could potentially have some very interesting applications. So let's start by putting down our picture that we had last time. So we've got our magnetic field here. This is uniform B field. And we've got a conductor, a metal bar going through it, has some length L, and it's moving with some velocity V. So metal bar, length L, moving through B. With some V. And V is to the right. Okay, so it's a conductor. So the bar has mobile electrons. So they're free to move around, like they're allowed to experience the forces of the universe around them, just like really all of us. And so these electrons, because the bar is moving, the electrons are also moving with some V to the right. So now we have moving electrons in a magnetic field and therefore magnetic force. So this is just a little recap of last time. So what is this magnetic force on the electrons? Well, we know how to calculate magnetic force. It's simply equal to the charge, which in this case is negative E, V crossed with the magnetic field. So V is in positive X and B is in positive Z. So it would then follow that F, magnetic, is in positive Y. If that's not abundantly clear, please take the time to prove this to yourself. So the magnitude of the magnetic force is equal to EVB sine of 90 degrees, which is equal to EVB. All right, so this is going to cause the electron C to shift upward. So this causes oh man, you should read that. So it's getting a force going in positive Y, it's going to start pushing them up. All right, so now we have our electrons getting pushed up in our bar. So this was the setup we started with. In a magnetic field, so here's our field. Here's our bar of L moving with V. And so now the electrons have been pushed up, which means this end is negative, and now this end is positive. So now that we have a positive end and a negative end, we're going to have an electric field in the bar. So if we just pull out the bar in more detail, L, it's negative, positive. And now we have a generated electric field from the magnetic force that's pushing the electrons up, generated in this bar. So you have a delta V. This also means, so this means the electrons are subject to both magnetic and electric forces. So now we've got the electric field in the bar, which is exerting an electric force, and we already have the previous magnetic field exerting its force. So time continues to pass. Our bar is just chugging along through that magnetic field, and it's at constant V. So our bar at constant V through B. And now we have a steady state. So now, steady state. So the question you might ask is, how is our induced electric field going to compare to our magnetic field? Will it continue to polarize? Will polarization increase? All right, so let's reason through this. So first, we have an upward force from the magnetic field. So this is going up. And the electric field is going to grow from this magnetic force. So our E field initially grows. From the result of this magnetic force. And then the electrons experience a downward force. So this causes the electrons to experience F electric, which is down. So F electric is equal to minus E times our new induced field. So now they have an upward force from the magnetic field, and they have a downward force from the electric field. And so eventually we're going to get a rather unsurprising result. So you're going to have that the electric field is going to be equal to V times B, which we've seen many times before. So eventually we'll get to a state where you no longer have forces causing the electrons to move. And so at this point you have equilibrium. So you do have a non-zero electric field at equilibrium, but the electrons are no longer moving. You have a constant velocity, so our acceleration is equal to the zero vector. You no longer have a current because E is equal to VB, and the net force is equal to 0. All right, so now let's look at delta E across the bar. So let's look at delta E. So E is equal to the drift velocity times B, and V and B are the same throughout the bar. So V and B are the same over the bar. And now E has become uniform, so E is uniform, which gives us delta V is equal to E times L, which is equal to VBL. So the positive end of our bar going back to our picture, so E is this direction. So the positive end of this bar is going to have the higher potential. It's moving downward in the bar against E, so therefore this moves towards higher potential. All right, so this is basically the gist of motional EMF. Now, motional EMF can be used to do something very interesting. So motional EMF can be used to drive a current. So we've induced an EMF by putting a conducting material at a constant velocity through a magnetic field. I know it sounds really contrived, but there's actually some really useful applications for this. So, and you've been able to induce a delta V. And so what could this bar basically act like? So we have a conductor with delta V, and so essentially we've got a battery. Sort of. All right, so it has, it does have maintained charge separation. As long as you keep it moving through that magnetic field. So, and in this case, going back to our thought model of the battery before, the magnetic force is acting like the non-Coulomb force. Okay. So let's bring this together and tie it with an electric current. So we need to do a little bit of an expansion on our little metal bar experiment. So let's say we still have our magnetic field. And now we have two metal bars on either end, and we're going to connect a little resistor between them. And we've got our initial conducting metal bar that's moving with some speed v, and let's say it's gone ahead and reached equilibrium, so we've got this side is positive, this side is negative. And we're going to work in ideal physics world. So these are frictionless metal bars. That's right. And what have I essentially built? So we've got a resistor, we've got conductors all the way around, we have a delta V here, we have a circuit. So this is a circuit. And we know all about circuits because we did chapter 18. All right, so it will have a current generated by the moving bar. So we'll have I generated by moving bar. This is motional EMF. All right, so we're going to break this down in a little bit more detail because it's really worth understanding. So we're going to start from rest into this state here. All right, so when we start from rest, so break it down. So the bar is at rest, and therefore EMF is equal to 0, and the current is equal to 0. All right, so to get things moving, you're going to have to apply a force. So something's going to have to move the bar. We don't really need to know what it is, but simply we know that some force started it. So we use F to get the bar moving, because it can't move without a force. I mean, we did study classical mechanics last semester after all. Okay, so moving, right along, the bar quickly becomes polarized. Like this happens really quickly. Remember how fast electric fields can get started into place? I mean, we've all connected circuits before, and like the bulb just bam, on. like really quick. So we've got our bar. And it's moving. And so let's look at the forces of the electrons on the bar. So we've got the electrons. So they want to move up. So the velocity is wanting to go up. We've got the velocity of the bar. So this is the induced velocity from the magnetic field. And then we have the magnetic force in that direction, which is equal to minus EVB. And then we have the magnetic force in Y, which is equal to EV bar B. So the velocity of the electron is equal to V bar in Y times V, the velocity that's moving upwards from the magnetic force, and 0. And so the magnetic force is equal to minus EV cross B, which is equal to minus EVB EV bar B 0. And as long as you apply this force, the bar is going to continue to accelerate. So we're looking at the situation of initial acceleration. So eventually, you don't want that. You want your acceleration to get to 0, and you want the net force to be equal to 0. So we're going to have the magnetic force in this direction and that force from U or something else in that direction. So we want to get to this state. All right, so and that's where we get to our original picture, its current state. All right, so let's look at that picture again. So we've got our magnetic field. There it is. And so we've got our resistor, the bars, which I'm just going to draw as lines. Picture gets a lot less fancy every time I do it. All right, so now we've got it so that we've got some constant V and some constant B, and this is going to keep going on. So as the bar moves, the charge separation is maintained. So now we're just maintaining charge separation instead of inducing it. And current is running through the resistor. So, just something to note. It's kind of interesting. So, we've got our electrons up here, and this side's more positive. The electric field is in this direction, and yet this is also the direction that the electrons are drifting up. Weird, right? Weird. Electrons going in the same direction as E. Well, it turns out that there's a very reasonable explanation for this. It's because what's pushing them up is that magnetic force. So FB is pushing the electrons up, and E induced is slightly less than the force that's pushing them up. And this is because electron current is running through that resistor, so it's being depleted. And so FB is just, the force to push them up is a little bit more than the force from the electric field that wants to pull them down. So, and this is, so if you recall, EVB is our force non-coulomb from that battery model that we did in chapter 18. All right, so the work of this force on an electron, so we've got force non-coulomb times that length L is EV bar BL. All right, so what we're trying to build towards is EMF. So we need work per unit charge. So we have work here, and so we can get to work per unit charge. So we have EV bar BL over E is equal to V bar BL. And so delta V is equal to EMF is equal to V bar times BL. So now we have our motional EMF. And this is, of course, assuming negligible resistance, R on the bar. If not, we know how to handle non-ideal batteries. So if that's not the case, delta V would be equal to this EMF minus R internal times I. So that would be V bar BL minus R internal times I. So there you go. And so EMF, this EMF has been generated by moving that wire in a magnetic field, and this is our motional EMF. And it tends to be very small. All right, so now let's express the work required for motional EMF in terms of power. So we want to look at work required in terms of power. So if we recall, force non-coulomb, L is equal to E V bar BL, and in delta T, the bar moves some delta X, and so we must supply energy at a rate of F delta X over delta T, which must be equal to F V bar. And so power is equal to IBL V bar is equal to I EMF. And so this is the basic principle of electric generators. So mechanical power is converted into electric power. So this is why motional EMF is so important. This is how power plants work. All right, so that concludes part 1 of Thursday's lecture, and I'll see you for part 2.